Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of semiconductors. So it's actually a dataset about the manufacturing process for semiconductors. And basically each semiconductor has gone through some sort of quality assurance test. And at the end of all these, we actually anonymized features. We don't know what. I think they're sensor readings from various sensors. But after all of these readings, which we aren't actually sure what they are, we have a pass-fail column, and we're going to be trying to predict this, whether a given semiconductor will pass or fail this test. So I would like to point out that in here, it tells us that they wrote it as 0.1, but I assume it means -1. That a -1 corresponds to a pass and a 1 corresponds to a fail. So I'm going to assume that the -1 means it passed, and the +1 means that it failed. Because we also have fewer examples, it's a very imbalanced class here. Very few fails. We would expect more would be passing than fails. Alright, let's hop into the notebook. We're not using random forest, sorry, we're using a logistic regression model. So we're going to try to predict whether it will pass or fail using a logistic regression model. To work with the data, we're going to import NumPy and Pandas. For visualization, we'll use Plotly Express, PyPlot, and Seaborn. For preprocessing, we'll use the train test split function, standard scalar, both from sklearn, and then we'll use the random oversampler and SMOTE objects from imblearn, or imbalanced learn. For our model, we'll use logistic regression, like I said, and then we'll analyze the performance using a confusion matrix and classification report from sklearn. Let's go ahead and load in the data using pandas.read.csv. We can go and grab the file path to the CSV file up here. So I'll copy that in, and we can take a look. Alright, let's also take a look at data.info, although we won't be able to see column-specific stats because there's too many columns. Okay, so the time column, we have to consider the sort of purpose of this model that we're building. We want to build a model that can tell if a conductor will pass or fail a test based on a series of sensor readings. Now, we want this to be sort of time invariant, right? We don't want the time to matter. And in fact, if we wanted to use this on future predictions, the time would not serve any useful information. Other than that, maybe the model would spot some trend from more recent years than older years. So we're going to drop the time column, and we're going to focus on the sensor data and try to use all these 587 features to predict the pass-fail column. So let's start preprocessing. And I'll create a function called preprocess inputs. It's going to take in a data frame. For now, all it'll do is copy it over. And we'll get back the data and store it in X using that function, and we'll pass in data. So X is just a copy of the frame right now, but this is the one that we'll do all the preprocessing on. You can also see we definitely have some missing values in this data. Alright, so the first thing to do is drop the time column, because we're not going to use it. So df.drop time from axis 1. Now it's gone. Alright, next thing is, let's look at these missing values. So we know we're dealing with all float columns, 590 floats, one integer, one object. The object was the time column, the integer is the pass-fail column. All the rest are floats. So when we look at the missing values, we can use x.isNA for this. You can see a true will represent a missing value in that location. So we can then sum over the rows to get the total number of trues in a given column, which is the number of missing values in each column. Now, we can't see all of them, and in fact I don't even want to print them all out because there's just too many, but we can do some filtering by, instead of taking the sum, we take the mean. And what this will do is it'll add up all the trues in the isNA matrix and divide by the length of every column to give us the percentage of missing values in each column. So this is 0.3%, 0.4%, etc. And I don't want to go and manually check each one, so what I'm going to do is ask, are there any that are greater than 0.25? Meaning, are there any columns that have more than 25% missing values? And if any one of these is true, then we're going to remove that column. So we can figure that out by using this thing as an indexer for x.columns. We use the true falses to say, okay, highlight all the columns that are true. And so here they are. There's not too many. I think there's 32 of these. And these are the ones we're going to drop. So let's put this in our function. Say drop columns with more than 25% missing values. So df equals df.drop. We actually want to specify them up on this line. Paste that in. Instead of x, I'm just going to change it to df, and we're going to call these missing value columns. Then we can say df.drop missing value columns from axis 1. Alright, we're now down to 559 columns, but you should see there should be no more remaining columns with more than 25% missing values. Alright, so now that we've removed those columns with too many missing values, how about we try filling in the missing values that remain. Now luckily our job is easy in this case because we know we're dealing with all float columns, so we can just fill in with the mean of every column. So in here, let's fill remaining missing values. And so for every column in df.columns, now if I'm going to use df.columns, if I'm iterating through all the columns, I just have to make sure that this has no missing values in it. I should have checked this earlier actually, but let's just make sure. We want to make sure that the target column does not have any missing values. We don't want to fill those. Alright, so this will just give us the true false for just that column. We can then sum over the whole thing to get the total number of missing values, and that's 0. Okay, so we have no missing values in the label column, and so we're safe to do this. For every column, we fill the missing values with the mean of the column. So we take the column, we set it equal to itself with the fillNA function called, which allows us to fill all the missing values with whatever value we specify. We'll pass in the mean of the column. So dot mean. And this should fill all the missing values in the whole dataset. Let's just double check. We're going to type x.isNA and then sum both over the rows and the columns to get the total number of missing values in the whole dataset. And that is 0. So we have no more missing values. And then we can move on into splitting and scaling the data. Actually, one more thing I want to do before, we don't have to do this, but it'd just be nice to give text labels to the training examples. So just so it's more interpretable, we have -1 and 1 right now. Let's just change that to pass and fail. So df equals df.replace. Actually, sorry, we should just do the column. We take the pass fail column and call it equal to itself with the replace function called. Set it equal to itself with the replace function called. And we can pass in a dictionary that has the mappings we'd like to use for replacement. So anytime we see a -1, we'll map it to pass. Anytime we see a +1, we'll map it to fail. That was as what we decided earlier. It doesn't give, the information it gives. It says 0.1. I don't know if maybe 0.1 it was originally encoded that way. We're just going to assume this is the -1 that shows up here. Alright, so we run this, and the end now should have pass or fail as text, which is fine for sklearn, which we are using today. Alright, and now let's split the data frame. So split df into x and y. Y is going to be what we're trying to predict, so that's just the pass fail column. And x is all the rest of the data, so we'll drop the column from axis 1, and then we'll do our train test split. So now we're going to split the data into xtrain, xtest, ytrain, and ytest using the train test split function from sklearn. We pass in x and y, give it a train size, let's say 70%. So we'll send the other 30% of the data to the test set. We'll keep shuffle equals true. That'll shuffle the data before we make the split. And then we'll give it a random state so we can ensure the results are always the same. Alright, let's return this. So I'm going to return all 4 sets of the data and then get them back over here. Let's look at xtrain and ytrain. So these two comprise only 70% of the data, and you can see that this last column has been stripped off the end of the data frame. Now the last thing I want to do is scale the data. So right now all of the different readings are all in different units. Actually, I'm not sure about that, but all the columns have different ranges of values. And the model will perform better if all the columns coming in have the same range of values, because it will basically give every feature, every column, an equal chance of being useful. Especially with logistic regression, since every column gets a single weight, if you have a high value in a column relative to another column, the output from that column multiplied with the weight is actually going to be a lot higher with a much smaller weight relative to another column with a smaller value. So you can misproportionately represent certain columns if you don't scale it in some way. Alright, so we're going to use a standard scaler. So that's a standard scaler from sklearn. This will just give each column a mean of 0 and a variance of 1 by shifting and scaling the column's distribution. So we'll fit the scaler to only the train set, because we want to sort of pretend we don't have access to the test set when we're doing the pre-processing. And then we'll transform using scalar.transform the train set and the test set both. However, before I proceed, I want to point out that this function will return a numpy array. So I'm going to go in and turn it back into a data frame afterwards, with keeping the indices the same as they were and the column names the same as they were. We'll copy this over for xtest, and we're done pre-processing. Alright, so you can see all the columns have a similar range of values now. Most of their values will lie between -1 and 1. Actually, I did notice, look at this. There's all zeros here. So when you see that after scaling, I actually should have checked for this before. Let's see. The reason for that is because there is only one value in the original column. That way when it's shifted to 0 and scaled, well, there's nothing to scale. Everything just goes to 0, and there's no variance. So let's check for this. Let's take I'll take data, the original data set, and I want to check how many of the columns have only one value. I guess we could do this with a dictionary, but there's just so many columns. I was trying to think of a better way to do it. Or I'll do it with a dictionary. So we'll map every column to the number of unique values in the column. And we'll do this for every column in data.columns. Oh, I forgot the parentheses. Okay. Now what I'll how to do this? Yeah, there's some. We could actually turn this into a pandas series, or even a data frame is fine. This is annoying. What about a series? Okay. So the reason I made it a series is because I want to keep the indices without treating them with like a dictionary. So what we can do now is just check if any of these are equal to 1. And then, this is very confusing, but we will index it on itself. This doesn't need to be so interpretable. It says there's none. Interesting. Let's see. Equals 1, and then I'll sum this. Yeah, okay, it says there's none, which is interesting here, because let's look at xtrain. Look at the 5 column. Is it string? Dot describe. Look at this. They're all 0. Dot unique. There's only one value. Okay, I'm very confused now because... Oh! It may have been because of the missing values. Right, maybe the only other value was a missing value, so that's why it showed up as multiple. Okay, so this is annoying. I want to get rid of these. I don't want columns in here with only one value. Let's try doing this for X train instead. You know, I don't want to see just the train set. I want to see all the columns. So we're going to, what I'll do is I'll just return X and Y and then comment this out. And then get back X and Y over here. The reason X and Y is because I don't want to do the train test split. Because I want to see if there's one value only in the whole data set before I make the split. So we'll just change data here to X. Alright, there's actually 116 of them. Okay, those have to go. Alright, so what we'll do is we'll take this thing, which is this series, and we'll use this thing, which is the true-false indexer for when they're equal to 1, and we'll use this as the index here. I know that's impossible to decipher just by looking at it, but now we can type .index to actually get the column names that have only one value. So this is so annoying. Okay, I'm not gonna put this into the function. I'm just gonna save this. So let's call these single value columns. And look at single value columns as a list. And I'm just going to copy this. I know this is not the best way to do it. And it's all on different lines. Okay, actually we can fix that. Just drag this. That puts it on the same line, then put a space. Alright, this is terrible. Let's at least indent them nicely. I know this is very boring, but it's important. Alright, so in here, before we do the split, and after we fill the missing values, right here, remove columns with only one value. And I'm going to put this in, and this is single value columns. And we'll say df equals df.drop single value columns from axis 1. Okay, and then return these again. Alright, let's just check this for both xtrain and xtest. It still says there's 3 in there. There's 2 columns? They were in there. Wait a minute. Those columns shouldn't even be in here anymore. Why is 5 still there? Give me a second. I'm going to pause the video and figure this out. I don't want to waste your time. Oh, I see the issue. There's not a comma here. Why didn't that throw a syntax error? Okay. Alright. That was stupid. Right, hopefully now... Okay, there's no more columns. Alright, we finally did it. Okay, so now we've gotten rid of the single value columns. And we have our preprocessed data. So now we'll look at the class imbalance a little. So let's look at the class imbalance with ytrain.valueCounts. You can see we have many more passes than fails. We'll just quickly visualize this as a pie chart with Potley Express, the pi function. The values we're using is ytrain.valueCounts. And the values is the name of the series, just pass-fail. We'll also give the names to the classes, which should be in the same order as these. So pass, and fail, and we'll give it a title, class distribution. I'll also just set the width to 500. Alright, and fig.show. Alright, so this is basically what we see. You can see there's many more passes than fails. And so let's start by training a model with this class imbalance. For the sake of time, I'm just going to paste in this function I wrote to evaluate the model, which will just return the accuracy and then a confusion matrix and a classification report along with it. So I'm going to create this model, logistic regression, and we're going to fit the model to the train set, and then we're going to call this evaluate model function on the model, pass in the test set. So here it is. You can see we have 88% accuracy, but the model's sort of failing. Actually, the model's not doing too badly. Oh, interesting. Okay, so you see the model is having a hard time. It's putting all of its predictions into the pass. Now, I'm interested is that it actually is making some predictions for fail, about 26, but they're almost all wrong because the model's just so used to seeing pass data. There's so many more passes than fails. We can help this by using a technique called oversampling. So first we're going to do random oversampling. And I'm going to be using an object from the Imbalanced learn library, which has nice implementations of all these class imbalance approaches. I'm going to call it oversampler, and that's just going to be a random oversampler. And we'll just give this a random state. And we'll oversample xtrain and ytrain. I'll actually call these xtrain OS and ytrain OS for oversample. And using oversampler.fitResample on xtrain ytrain. So now let's just go in and look at this one more time. Now that they've been oversampled, we're going to look at ytrain OS. You can see it has actually sampled up. So what it did is it looked at the minority class. So it went into the fails and just duplicated random examples until we had as many fails as we did passes. You can see we've balanced the classes. Only problem with this approach is that you do have duplicate rows, and you're not adding any more information to the data set. You're just sort of tricking the model into thinking it's seeing as many examples in each class. So there's another way. Oh, actually, we should evaluate this. So I'll just copy from above. So here we're going to train on xtrain OS, ytrain OS, and evaluate on xtest. Actually, xtest. The test set stays. All right. So this is actually a performance increase. So we look over here. We had an F1 score of 0.94 in the pass and 0.19 in the fail. Now, we were already doing quite well in the pass, but our fail class was not doing so well. Down here, it's not much of an increase, but we did get our F1 score go up. We lost 0.01 in the pass, but that's okay because we're already doing really well in that one. We need this one. We need to increase the performance of the fail category. So I'm going to try one last thing, which is oversampling with SMOTE. So the SMOTE algorithm, basically what it does is it looks at the train set, and picks a random training example, then finds its 5 nearest neighbors, or some k nearest neighbors, picks a random neighbor, and then picks a random point on the line between those that training example and its neighbor. And then it creates a new data point there. So it's creating synthetic data in the same region as the original data. Now this is a little better, in my opinion, than the random oversampling, because you don't get duplicate columns, and you're putting synthetic information into the data set. Now all the information you're adding is actually just derived from the original information, and it is sort of fabricated, but sometimes you can get better performance with this. Not always. Sometimes random oversampling actually outperforms it. We should take a look at both of them. So let's just copy this over. Instead of using random oversampler, I'm going to use SMOTE, and we're just going to change OS to SMOTE. Alright, then the class distribution will be the same. I won't do another pie chart, but I'll just show list of value counts. Oh, sorry, Y-train SMOTE. It's been upsampled, oversampled, so that they have the same class distribution. And then we'll do this. Look at the model's performance. Just change these to SMOTE. Alright, and so it looks like this is performing worse. We actually got better the best performance comes from the random oversampling in this case. You can see our F1 score went back down to 0.19, and this one went down to 0.92, which is the worst so far. This is actually doing better. So in the end, random oversampling was best here. Alright, that was today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.